Yep. So our next speaker is Alex. So I'm going to add you, Alex. So Alex is here to talk about the well-tempered mesh, Linkerd, Zero Trust, and the application. And I really like that. I really like that title, the well-tempered mesh. I'm going to talk about well-tempered stuff all day now.
Exactly.
Welcome, Alex.
More well-tempered.
Thank you.
Thanks, and keep the questions coming, everyone. You're doing great.
All right.
Thanks.
So Alex, I'm going to add your slides and duck out, and off you go. Thanks.
All right. Thanks so much. All right. Hi, everybody. Glad to be here. My name is Alex. I'm going to be talking about Zero Trust and Linkerd. So specifically, we've been talking a lot about Zero Trust today, Zero Trust Day. So I wanted to talk about what that means from the context of a service mesh. So I work at Buoyant. I am one of the maintainers of Linkerd, the service mesh. And yeah, why don't we get started? Okay, so here's what we're going to be talking about today. I'm going to start off by giving just a very, very quick introduction to Linkerd. So hopefully we can all kind of get on the same page about what Linkerd is and what a service mesh is, and why Zero Trust matters in that context. And then kind of dive into some more of the details around Zero Trust and what does that mean for us? How is it useful? What does it protect you from? And how does it kind of work at a nitty-gritty layer? And so trust and identity are two concepts that are very, very tightly intertwined. So we're going to talk about both of those and how they relate. And so kind of armed with that information, I'll be able to show a little bit of a demo. We're going to be using that same faces demo again to show how these concepts apply in a service mesh to an application. And then hopefully leave a little bit of time for questions at the end. Okay, so here's a very quick introduction. Or refresh if you already know. Okay, so Linkerd is a service mesh, and that means that it is a layer for providing a bunch of infrastructure concerns to an application running in Kubernetes. So in particular, things like security, reliability, and observability, and providing those at a platform level rather than needing application developers to build these things into their application. Traditionally, if you wanted to do things like TLS between services or automatic retries or to instrument your application with traffic metrics, that's all stuff that you would either have to build manually in your application or pull in through a library or something like that. And so what a service mesh lets you do is it gives you all of that functionality, but it gives it to you in a way that's uniform across the entire application. So this means that even if different pieces of your infrastructure are written in different languages, you've got, like a polyglot architecture, or they're using different libraries or whatever, you still get this uniform layer across of everything. And it also means that there's no application changes required in order to do that. So you don't need to bother your application developers to implement all of these things. You just kind of get it uniformly in a way that's transparent to the actual application. And it also gives you this nice separation of concerns where the application developers can focus on what they want to do, and you can have something like a platform team or a DevOps team or something like that managing that platform layer with all those security, reliability, and observability concerns. So the way we do this is with a sidecar proxies. So every pod in your application is going to get an additional container in that pod, which we call a sidecar. And that container is going to be a proxy, which intercepts all incoming and outgoing traffic from that pod and does all of these cool traffic management features onto it. So it'll do things like collect traffic metrics on that traffic. It'll do initiation and termination of TLS and all kinds of other cool stuff. And so we call that set of pods, or sorry, that set of proxies all taken together, we call that the data plane, because that's where the data is flowing. The data is flowing from one pod to another, and it's going through these proxies that are on either side of it. And then in order to manage those proxies, we have something called the control plane, which is responsible for kind of managing all of those proxies. So it's making sure that when a new pod comes up, it gets that proxy added to it as a sidecar container. It does things like give those proxies the configuration they need. It gives them the service discovery information they need. And in particular, what we're going to be talking a lot about today is it gives them their certificates and identity. which is going to be used for zero trust mutual TLS. So I talked quickly about security, reliability, and observability. Those are kind of the three categories that most of the service mesh functionality falls into. When we talk about security, we're usually talking about automatic mutual TLS between pods. So when two pods talk to each other, they have that secure connection. But there's also a lot of reliability features, retries, timeouts, traffic splits, and many others, intelligent load balancing. And then a bunch of observability features, gathering all of these metrics about your traffic, things like request rate and success rate and latency, and gathering that all up and exposing it in a format that can be scraped by something like Prometheus and aggregated and queried. So you can get very, very rich data about your call graph, about the performance of your services, without needing to instrument them in the application itself. Okay, so what does zero trust mean in this concept, in this context? So Linkerd or service mesh is fundamentally about managing traffic. So when a connection or a request goes from one pod to another, we want to do stuff with it. And one of the things we want to do is we want to check access and make sure that that is a connection or a request that should be allowed to go through. And so with this concept of zero trust, that means that we want to check every access every time. We don't want to ever just assume that something coming in should be allowed. So in the diagram, we've got that red arrow saying here we've got a request coming in from one pod to another. How do we decide what to do with it? And so there's a few different things here that we want to make sure we're enforcing. So one thing is identity. We want to know who we're talking to, and this applies to both the server and the client. The server needs to know who the client is that's connecting to them, and the client needs to know, well, I tried to connect to the server. Am I actually talking to who I think I am? Or has my connection been somehow stolen or redirected, or is it being spoofed? We need to know with a lot of confidence that we're talking to who we think we're talking to. And we also want these two other features, encryption and integrity. We want to know that when we're sending data on this connection, no one can, no other unauthorized party can listen in on that connection, read that data that they're not supposed to. And we also want to know that they're not going to tamper with it, that this data, if we receive it, we know that it's the original data that the sender sent to us and it hasn't been modified in any way. So the request can't be altered or eavesdropped upon. And then even past those things, we also want to know, well, okay, now we know that this connection, we know who it's from, and we know that its contents are valid, but we still might not want to accept it depending on who the identity of the client is. We might want to say, well, I know who you are, but I don't trust you, or I don't think you should be allowed to make this call. And so that is a layer of policy where we say, okay, we know who you are, but now we need to know whether, how to act on that information. Is that okay for you to make that call? And so in order to get encryption, integrity, and identity, these are all things that are we get from the industry standard mutual TLS. So these connections are encrypted with TLS, and the M, the mutual part of TLS, means that both sides have to provide cryptographic identity and say, hey, here's who I am, and I can prove it cryptographically. And so both sides know who the other side is. And one of the really cool things about using a service mesh like Linkerd is that you get this automatically. There's no configuration needed. The application doesn't need to, opt into this in any way other than by being part of the service mesh. They don't need to manage certificates or identity or any of that stuff. They can just talk to another pod as if they're making plain text requests, and those proxies on either side will automatically initiate TLS on one side and terminate it on the other. And so you get encryption, integrity, and identity for free, which is really cool. The place where you start to need configuration is at the policy layer. So once you know who you're talking to, we can't automatically know whether that's okay or not. That needs to be something that's specified. And so Linkerd has a set of custom resources for describing these policies so that you can say, who should be allowed to talk to who. So I think the main ones that we're going to be talking about today, there's server, which is a custom resource which defines a traffic receiver. So on one end, say this is a place, a port, and a set of pods that might receive traffic. An authorization policy, which is a resource that describes what things should be allowed to talk to that server. And that's going to be phrased in terms of identity, and I'm going to talk about that more in a minute. And then we also use the HTTP route resource inspired by the Gateway API so that we can make this policy even more fine-grained. And we can say, well, maybe we want different policies for different routes, and say that this route is open to the public. This route requires, can only be reached by other pods in the mesh. This thing can only be reached by very specific identities. You can have this very fine-grained policy per route. Okay, so that's the idea. How does it work? So we've been talking a lot about identity and saying that these, when two pods communicate with each other, they need to know who the other one is, what the other's identity is. Well, what do we mean by identity in this context? And when we're talking about identity in the context of a service mesh, we're talking about a cryptographic identity, which is represented by a certificate. So if you're familiar with public-private key cryptography, this should hopefully be a little bit familiar. Each pod will have a certificate, which is kind of like its public key. It tells other actors what its identity is. And then it also has a private key that it doesn't tell anyone, keeps totally to itself, and it uses it to verify and connections that it uses. So these identities, these certificates that I have are derived from Kubernetes service account tokens. So the service account becomes kind of the unit of identity. When a pod needs to get a certificate in order to participate in mTLS, it sends its Kubernetes service account token to the control plane to prove its identity. And the control plane says, okay, yes, I can verify you are who you say you are because of your token. Now here's a certificate that you can use. And that certificate will have a name in it, which is derived from the service account name. And we can use cert-manager to make all of this certificate management, excuse me, a little bit nicer, but we'll talk a little bit more about that in a minute. So these certificates they're just X509 certificates. So this is very standard, kind of industry standard for doing TLS. But they still are a lot of work to manage because there's a lot of certificates in play here. Every single pod in your mesh needs its own certificate. And not only that, but there's going to be a trust hierarchy where the control plane also needs certificates. And so there's this kind of multi-level trust hierarchy where the pod certificates are signed by the control plane, and the control plane itself needs to be managed by something else. And so it gets rather complicated. And so I'll show you how that works. Okay, so in Linkerd's kind of model of how certificates and signing works, you have multiple layers going on. So here at the bottom, we have all of our workloads, all of our pods. Each of those has a workload certificate. Sometimes we call these leaf certificates because they're kind of at the bottom of the trust hierarchy. And these certificates are what they use to communicate with each other. Every time they do a TLS handshake with another pod, they're using these certificates to establish that TLS connection. Oh, I have lost my camera feed. That's strange. Sorry about that.
No, yeah, you've gone missing.
I've gone dark.
We can still hear you, which is a good thing.
Yes.
Okay, let me see if I can get that camera back, and if not, I'll just have to proceed as a black square.
Or we can bring some. You're getting a lot of questions in the chat. I see Catherine is answering some of them, but if Catherine or somebody wants to come on and manage some of the questions while oh no, there you're. Oh, you were back for a quick minute.
There you
Am I
are.
back? Oh, okay, fantastic.
Yeah.
All right, sorry about that.
No worries.
Do you want us to ask any of these questions before you move on, or wait to the end?
Why don't we take them at the end?
Okay.
Just in case I'm going to answer any of them kind of as I go.
Perfect.
Okay, so let's see. What was I saying? I was talking about these workload certificates and how they're used to sign the TLS handshake that's used between these pods. What's kind of cool about these is that since they're used all the time, they're used basically for every piece of traffic, they are kind of at higher risk than they otherwise would be for being compromised, right? They're in use, so something could happen. So we want to bound the lifetime of these certificates to kind of protect ourselves in that scenario. If these certificates are somehow compromised, if these private keys are somehow compromised, we want to limit the damage and say that these are kind of short-lived. So these certificates, I think by default, are valid for 24 hours. It's configurable, but I think 24 hours is the default in Linkerd. And after that, those certificates are no longer valid, and those pods will need a new one. And so there we go. Back to my slides. We have the control plane, which is issuing these certificates, needs to issue a new one. So there's this concept of like refresh or rotation, where on a regular basis, these pods can reach out to the control plane and say, hey, my certificate, which is only valid for 24 hours, is about to expire soon. Please, before it does, I need a new one. Here's my service account token to prove that that's allowed. Please give me a new one. And so this all happens kind of automatically. These pods will be continuously refreshing their certificates from the control plane as needed, and that's great. But in order to do this, of course, the control plane needs its own certificate and private key in order to generate and sign these certificates for the data plane. And so in order to do that, there needs to be kind of a trust authority or a certificate authority, which has generated the certificates for the control plane, right? So you've got the data plane down at the bottom, you've got the control plane there in the middle, and then at the top you kind of have this concept of the root, which lives even above that. And there's these dotted lines drawn here. These represent Kubernetes clusters. You could have, a common root between multiple clusters. And in fact, that is the way you need to do it if you're going to be doing multi-cluster communication with Linkerd, where you've got Linkerd installed on 2 clusters and are using the multi-cluster extension to communicate between them. They need to have that shared trusted root so that they can communicate securely between the two. But the other thing that means is that trust anchor part can live outside of Kubernetes. And it's not involved in the day-to-day signing of traffic, so it can be kept very secure. So if you installed Linkerd kind of just in the most default way from the CLI, this trust anchor is a self-signed certificate, and it lives outside of Kubernetes, so it's not hopefully at risk of being compromised the same way something in Kubernetes is if that cluster were compromised somehow. And we talked about bounded lifetime at the bottom for those root certificates. We said that those are only valid for 24 hours at a time by default. The same thing applies at the next layer, where these issuer certificates also have a bounded lifetime. It's typically much longer, although again, this is configurable. I think the default is 1 year. So these certificates are valid for 1 year. After that 1 year has passed and those issuer certificates, that middle layer starts to expire, they need to be replaced, just like at the bottom. But unfortunately, this is a very manual process, right? Because again, those trust anchor credentials, which live outside the cluster, are not managed in any way. So there's a manual process, which is described in the Linkerd docs, for how to generate new issuer certificates when your issuer certificates are about to expire. And you need to dig out that original key you used, when you're first setting up your cluster, that you never, shared with anyone, you kept very secure, hopefully, to generate new issuer certificates. So this is a really nice system because it kind of isolates each layer and has kind of scoped a lifetime. So you've got like the shortest lifetimes at the bottom and the longest ones at the top. And the ones at the top are those keys are most secured. But it's very inconvenient. It's very manual, right? It's a very manual process to say, oh, it's coming up on a year. These certificates are going to expire soon. I better dig out the root private key and generate some new ones. Maybe not something you want to be doing manually. So cert-manager can be used to automate this, and it's kind of perfect for this scenario. So in this diagram, all those gray certificates are managed kind of by hand. the control plane automatically manages the pink ones. But if you add an extra layer to this diagram and bring cert-manager into the picture, things get a lot more automatic and less cumbersome for the operator. Right. So if you then have cert-manager, you introduce cert-manager. Cert-manager can be configured to do these automatic rotations on whatever period you have. So if you have cert-manager managing your trust anchor, and you've got your issue certificate, and you configure cert-manager to automatically rotate all of those things, then you no longer need to do that manually. And of course, cert-manager can be hooked up to whatever PKI infrastructure you have. You can either have cert-manager use its own self-signed root, or you can hook it up to some other root system, or put credentials in Vault, or do whatever you need to do. Do whatever makes sense for you, and that'll all just kind of flow through. Okay, so to summarize that, certificates expire, and this is by design. This is a kind of a very important security property, that they only live for a certain amount of time, so that if they're compromised, that's not going to compromise your system forever. And they're also kind of bounded in scope. You've got your individual leaf certificates, which represent a single identity, a single service account in your mesh. Anyone compromising those credentials basically can impersonate that identity, but they can't, that's the limit of what they can do. And then, at higher layers, once you get up to the issuer, then if that's compromised, they can issue certificates for different identities in the mesh. And so you've got these kind of like layers of danger. But since these things expire, we of course need to replace them before they do, so that the system can keep working. And that can either be done manually, which works perfectly well. But if you don't want to have this recurring manual process, you can use something like cert-manager to automate it. And I believe the next talk is going to go into actually a lot more detail about how cert-manager can be used to automate this kind of certificate rotation. So stay tuned for that. So let me show you this kind of in action. So here's the demo architecture that I think we've been looking at all day. There's the faces application. So this is a multi-cluster, or not multi-cluster. This is a microservice infrastructure where we've got kind of a main face application, and it calls two different backends, Smiley and Color. And we have the browser, of course, which calls into the cluster to reach the face service and get this web page. So we're going to be talking about how to lock this down. We've got an ingress, which is how things get into the cluster there. And then we also have all of these services are in our service mesh. So that means that all of these connections are protected on both sides by Linkerd. So they've got a Linkerd initiating that connection, and a Linkerd proxy on the other side terminating that connection. So you can see by these little lobsters here that there's a service mesh protected connection from the ingress to the face app, from the face app to Smiley, and also from the face app to Color. So all of these connections are going to be mTLS'd automatically, and are places where we can also enforce policy if we configure it. So let's see that. Okay, so I've got my terminal here. Let me just pull up my cheat sheet. Okay, so here's the same application we've been looking at. It's the Faces app. Everything looks good. So this is coming in from the outside world through the ingress into the cluster, and everything is happy. But we want to lock it down. We want to be a little bit more restrictive in what we allow to call what. So just from the terminal here, I can call into this cluster on the command line using curl. So if I do a command like this, so this is curling into the cluster, and I am hitting the /face endpoint here, which will hit the face service. That's face front end. And I'm just looking at the return code, the HTTP return code here. And hopefully, there we go. We get a 200, so we're able to call into that face service. We can also call into these other services in the cluster. We can call into Smiley. We can call into Color, because there are routes defined for these in our gateway. So we can kind of route to all these different services. Okay, so that's okay. That's cool. But we really want to lock this down. So Linkerd is there. It's putting mTLS on all these connections, but it's not enforcing any policy on them. So it's saying, well, we know who everyone is on both sides of these connections, but we're just, once we know, we're going to allow it because we don't know what should be allowed and what's not. And in order to really lock this down, what we can do, kind of the most extreme things we can do, is we can add this annotation called config.linkerd.io/default inbound policy equals deny. So we're putting a default deny policy on here, which means that we're saying all connections should be refused unless explicitly authorized. So unless we specifically have a policy which allows this connection to go through, we should deny it. And in order to pick up that change of default, because this is changing the default behavior, we need to restart that deployment. I'll just restart that really quick. Oops. Faces. So those have restarted. And if we look back at our browser, we can immediately see things have stopped working. As we would expect. This is not surprising. We have said to reject all connections unless we authorize them, and we haven't authorized anything. So everything has stopped working. Excellent. Okay. And if you remember our architecture, there's actually two different places where we need to now add policy to authorize connections in order for things to work. We need to add one authorization to allow that ingress, that API gateway, to call into the Faces app. And we also need to add an authorization that allow the Faces front end to call into those two backends. And so we need to do both of those in order to kind of restore functionality here. So let's take a look at one of the resources we could add to make that happen. So this is a server resource here. You can see the kind is server. We call this the Faces front end. And so this is a server resource, a server policy resource, which describes the front end. And so I said earlier very quickly that a server selects a set of pods and gives a port. And so we can see that here, there's a pod selector, which says this is going to select all the pods where the service label is either face or Faces GUI, and the port is the named port HTTP. So it's going to look for a port named HTTP on any pod that has the service equals face or the service equals Faces GUI label. And this is not going to do anything, but it's going to define this as a server. It's going to define this as a thing that receives traffic. So we can apply that resource to create that server. And now that we've defined that, we can define the policy to allow traffic to it. So this is an authorization policy resource. And this is what's going to actually authorize that traffic. So this authorization policy has a target ref, which targets where the traffic is going to. So in this case, it's that server that we just defined, that Faces front-end server. And then you can give it a list of required authentications. And in this case, we are giving it an authentication called mTLS authentication. This means that we're going to be looking at the identity, the zero trust cryptographic identity of the client. And we're saying that it has to match this name here. So what you can see from this name is very long, but you can see that it's derived from service accounts. And the service account that we're looking at here is Emissary-ingress. So altogether, this is saying that we're going to authorize traffic that to the Faces front end as long as it has this identity, this certificate, Emissary-ingress. So let's apply that. And what we can see right away is that something has changed here in the application. We're no longer getting those grimacing faces, which means that we weren't able to connect to the front end. We're now getting these angry faces, which means that we were able to connect to the front end, but the front end was not able to connect to those back ends because we haven't authorized that part yet. And so in order to do that, it's very similar. We can create a very similar server that represents those backends. So here, this one is called Faces Backend. It is a server resource. It selects any pods where the service label is color or smiley, and the port is named HTTP. So we can create that service very quickly, or that server, I mean. And then likewise, we can create a authorization policy to allow traffic to that server. Oops. Here's the authorization policy. It targets that Faces backend server. And it says the required authorization is, again, mesh TLS. It needs any client to have this identity, this certificate. So the face service account is the only thing that's going to be allowed to talk to those backends. So we can apply that. And we immediately see things go back to green here in the application. Now we've got all of those connections that we wanted to authorize are now authorized, and things are working again. So hooray. And one thing that we can check here is that even though we had those routes earlier that we defined that let us kind of call in through the ingress directly to the backends and kind of skip that front end, what we'll see is that won't work anymore. So if we do something like this, so this is a curl, that same curl request where we're curling into the face service. So here's /face at the end of that URL. That works, we get a 200. But if we try to call into one of those backends directly from the ingress without kind of going through that face service, that face front end. So if we try to go to, for example, Smiley, we get a 403 denied. And then same thing for color. And that's because, you know, what's happening here is we have these ingress routes defined where the ingress will try to route to one of these backends directly. But even though we have that route defined for the ingress, we don't have an authorization policy. So there's nothing that authorizes that connection. And so Linkerd says, hey, I know who you are. You're the ingress. That's fine, but you're not allowed to talk to me. So I'm going to reject you. And so kind of going at it from this model where things are kind of denied by default is a much safer way to organize things, because even if bad actors get into your cluster, you know, unless they have the right identity in order to talk to a service, they won't be able to do it. And so that gets things to be much, much more locked down. And there's a lot of other cool stuff you can do with this too. I mentioned that you can do per route authorization. So you can allow routes, certain routes to be more open than others. You can have different routes need different authorizations in order to talk to them. And that's built on the HTTP route inspired by the Gateway API. It's very, very cool. So let me jump back to the slides real quick. Okay, so that's kind of all I wanted to show off. Hopefully there's a little bit of time for questions before I get into that. I just wanted to quickly plug that Linkerd Day is coming up. This is one of the 0-day conferences at the beginning of KubeCon Europe. So this is kind of a full day of talks that are going to be very, very cool. I was on the program committee for this, or I am on the program committee for this. So I've seen how good these talks are. They are all from end users. There's no vendor talks. So that's really, really cool. Kind of hear it directly from people who are using this software. So I highly recommend checking that out. And there's also Service Mesh Academy from Buoyant. This is a self-paced service mesh course and certification. So for anyone who is using Linkerd in production, or who would like to be using Linkerd in production, or is just curious about it, this is really, really valuable information that you kind of need if you're going to be doing this in real life. And there are also monthly hands-on engineering-focused trainings directly from the creators of Linkerd. The next one coming up is on May 18th on circuit breakers and dynamic request routing. It's a deep dive. I know this one's going to be really interesting. This is one of our most requested features for Linkerd, new in 2.13. So I know this is going to be a really popular session. Highly recommend you check it out.
Okay, thank you, Alex. We are running a little bit behind, but we have so many great questions. We're just going to hopefully ask you a couple. We know Jason and a lot of folks have been in there answering them already for you, but Ashutosh asked so many great questions, so I want to highlight at least one. Does Linkerd provide any prompt alert if anything goes wrong with cert rotation?
Yeah, that's a great question. So if things go wrong with cert rotation, first of all, you'll see it. You'll see it in the traffic because things will stop working. But there's also a lot of Kubernetes events, like warnings that are emitted through the Kubernetes event system that indicate when cert rotation is successful or fails.
Perfect. Okay, we've got another one. One more. Can we use external CA with Linkerd?
Yep. Yeah, absolutely. And that's kind of what I was talking about when I was talking about using cert-manager to do cert rotation. You could certainly use other things other than cert-manager, but that's the most common.
Okay, great.
Awesome.
And most of the other questions, if not all, were answered, but I'm sure more will come in. So if you can hang out in the chat and
absolutely.
keep answering, I'm sure there's some great questions. Hi, Todd, by the way. Good to see you joined us again, and thanks for your question. It's nice to see when friends and community members show up. So with that, thank you so much, Alex. And let's see.
Thank you.
Thank you.